Okay, Bismillah. Today we're going to talk about graphs and transformations, the fourth chapter of the Pure Mathematics 1 syllabus. And first point that we're going to cover is cubic graphs, which follow this standard form of ax cubed plus bx squared plus cx plus d. So if we were to graph this function, if the coefficient of a, or the number next to x cubed, happens to be greater than 0, or in other words positive, this is how it will generally look like. And obviously it doesn't have to strictly follow this form. This is only for ax cubed, so that there is no other like numbers with it or whatnot. But usually it could look like, it could look like this. I mean, I don't know why my tablet is acting up. It could look like this, or it could look like this, but either way, the general form is that it's going to follow some sort of shape like that. And the second type of graph within our cubic is also when a, or the coefficient of x cubed, is less than 0, aka negative, and it's going to follow this form. And as I said, it could also follow this form and whatnot. So it just has that kind of like shape to it. We're going to solve questions either ways, and we're going to understand more how to solve cubic functions. So the function that we're given, so we can graph, is y equals x, and then two brackets of x plus 1 and x plus 2, and we're asked to graph it. So when it's factorized in this form, we could already tell what the roots will be. The roots here will be 0, this will be 0, this will be -1, and this will be -2. So if we were to just draw a graph roughly, and let me just draw it properly. Yeah, we have 0, -1, -2. So we have 0 here, we have -1 here, and -2 here. And we could tell that either ways, the coefficient of x cubed is that if you were to just multiply each here, it will all be positive. So we're going to generally follow this type of like shape of the graph. So we could just tell that it will look something like this. But obviously, we not know what exactly the turning points will be. And this is just additional, by the way. You could roughly draw this. You don't really need to get the turning point of this graph. In the end, to actually get the turning points, as I said, you just set the derivative you get to 0, and you solve for x values. But either ways, so the first step we do is we get the roots of the graph, and we already established that by already having our functions factorized for us. So we have the x values, or the roots, to be 0, -1, -2. And now we have to find the y-intercept, where this function, or where this graph will intersect the y-axis when x is to 0. So we can already tell that if we already set this to 0 to find the values of y, or the y-intercept, the whole thing is going to equal 0 in the end, because 0 times anything else will be 0. And in the end, it will look like this. But just to make sure, I not know if the turning point will be below or like just something like that. I don't know. This is the first time I'm doing it. So if we were to say that we have their points 0 and -1, -2, and we know that this is all right. It has to be like this portion of the graph. But what about the second portion? Where is the turning point? Will it be all the way down, or will it just kind of lay across, or just slightly graze the x-axis? We don't know. So if we were to just pull up our calculator, and let's just get -0.5, a number between -1 and 0. We don't really need to get the turning point exactly. We can just graph it roughly. So if I were to replace each x in the function as -0.5, so I have -0.5 times -0.5 plus 1 times -0.5 plus 2, we'll have -3/8, which is very close to 0 if you really think about it, just -0.4 roughly, or like approximately, somewhere here. So we can just slightly, and this is what it will look like. So yeah, here's the graph for you. So yeah, there we go. And keep in mind, you have to kind of add the curves when drawing. Like you cannot just, like I cannot just do this, you have to adjust the curves to it, or yeah, just roughly like that, you know, just make the curves obvious. Obviously here I could have done it more than angled, so it could just go like this, but yeah, you get the point. I don't think so they're going to really like deduct marks on how the curve looks like, but at least you follow the general form or shape of the graph. So yeah, just as a quick summary on how to graph cubic functions is that you first of all establish the roots you have, you get the y-intercept, and you try to deduce or visualize how the turning point will appear. Okay, second function that we're asked to graph is y equals x squared, x cubed, my bad, minus 2x squared minus 3x. We could obviously factorize this with a calculator and there won't be any issues with that, but what I want you guys to notice is that there's no d term, aka the y-intercept. So we could already know that this graph will hit the origin, or it will at least pass through the origin. And we could easily factorize this. You know, we could just take x as a common factor. You don't need to do this, by the way, you could just do it in the calculator straight away, but this is just for yourself. You have x squared minus 2x minus 3. And now you can just get the factorization of, excuse me, of x squared minus 3x minus 2x minus 3. So if I just plug all these in the calculator, I'll get 3 and negative 1. So in the end, the x or the roots basically will be, obviously we will not forget x equals 0. And we have x equals negative 1 and x equals 3. So these are our roots for this graph. So let's just draw a graph roughly. We have 0, we have negative 1, and we have 3. And there's no y-intercept. So in the end, as I said, if the coefficient of x cubed is greater than 0, which is aka positive, it's gonna follow this general form, like this. So in the end, if I were to look at this graph, and obviously 0 is one of it, so I know it's going to look like this. And there's no debating it. You could argue, oh, what about the turning point? You don't really need to get it exactly. That's how it will kind of look like. So yeah, I'm pretty sure it cannot get easier than this. Graphing cubic functions is not that big of a deal. And we could say that we kind of already covered it. Moving onwards, we're going to talk about reciprocal functions, which follow the form of either any number k over x and k over x squared. So the first form of reciprocal function we're going to talk about is k over x, or basically the exponent of x is 1. We have two forms of it generally, when either k is greater than 0 or positive, or is negative and less than 0. When it's greater than 0, it generally follows this form. And k is just basically, you could say, the amplitude of the function. It determines how far like these will separate from another. Let's say if k was a small number, let's just say 1 over x. So generally it will just be something like this. You'll find that it will tend to be closer to the axis. However, if you were going to say 12 over x, for example, you find that no, it's actually going to get further away from each axis. So you could just imagine k to be like the amplitude, or the number which determines the amplitude of the function itself, or of the graph. And yeah, this is generally the look of it when k is positive or greater than 0. And moving on, when you have, excuse me, I'm very sorry about that. And k over x, and in this scenario, it's when k is less than 0, aka negative. And keep in mind, how can I say this? Whenever you add a negative sign to the entire function, so let's say if k is here, as I said, greater than 0, and in this case it's negative, all you do is you just actually reflect it along the y-axis. If we put them side by side, we'll realize that they're just reflections of one another, and the only difference there is that if you look at them algebraically, It's just a negative sign. So just as like a quick heads up or a quick tip is that if you have a function, two functions that are basically similar, but the only difference is that one of them has negative like over its entire thing, there's just basically reflections along the y-axis. So yeah, as I said, if you put them side by side, they're technically very similar to one another. I'll draw k over x right now, which is basically this. And yeah, there you go. They're just reflections of one another. So this is for the, and this is the look when you have k to be negative. Now let's move on to k over x squared. And obviously in both of these cases, very self-explanatory. I don't think so I really need to say much. You just kind of know that, like example here, this is when k is greater than 0, and you just have it reflected along the x-axis this time, unlike the y-axis when we had the power of x to be 1 when it's in its reciprocal. So now let's solve some questions so we could reaffirm what we just went through. So we have y equals 4 over x, which is basically a reciprocal function, as we said, and k, or 4 as we have it here, is greater than 0. So now we know this is the general outlook of it. It's going to look like this. However, let's just get some points. Let's just determine some x coordinates we have, so we can generally know how far, like the amplitude basically of this function. So basically we know that at 4 over 4, when you have x to be 4, basically it will be 1 here. And 4 over 2, if we were to say that here is 2, I don't know why is it like that, and here is 4, for example. 4 over 2 is basically 1, and we can just say it's going to go along like this, and it will never touch the x-axis, the y-axis in this case. It tends to go to 0, because if you keep increasing the if you keep increasing or decreasing, it depends. Like if you go along here, it will generally keep going up to infinity. However, it will never actually touch the y-axis. And also in this case, if we move along the x-axis and we keep increasing our value of x, y will keep getting smaller and smaller. However, it will actually never touch 0 as well. So you can just say that they're both going along positive infinity in each of the respective axes. And also here will just be a reflection, so you can just kind of imagine it to be somewhere something like this. Okay, next question is just the negative reciprocal of x. So we have negative 1 over x, and this is very self-explanatory. I don't think I really need to say much. As I said, there's a negative over the entire function itself. So we could just say that it will be a reflection along the y-axis. So it will be like this and like this. And yeah, that's, I don't think so there is any difficulty in that. Moving on, let's go to the reciprocals, where we have x squared as a reciprocal, or denominator, you could say. So as I said, this is generally the look of k over x squared when k is greater to be 0, as we have here. So let's just draw a graph, and it could be roughly, and in the points of 2, let's just arbitrarily assume that these points are to be 2, and we can just say that in here to be 1, and to just move along like this. Yeah, so there you have it. And obviously it will be the same if you have negative, like it will just be like this, so it doesn't really matter. I think so this is enough practice on graphing reciprocal functions. Okay, next topic we're going to talk about is points of intersection, and we already talked about this like extensively in previous chapters, where I think so, if I could recall, simultaneous equations were actually, as I explained, that if you were to graphically visualize or symbolize what these simultaneous equations actually mean, you're just getting their points of intersection. So same thing here as well. We could equate these two functions together, since we're asked to, hence points of intersection, and we could find how many points of intersection there are, and this is obviously through equating them. So let's see, we have x bracket x minus 3 and y equals x squared bracket 1 minus x. Obviously, we could graph them and see how many points of intersection they'll have, and then we could solve for their points of intersection. So let's do that. Let's actually graph each one. I think so. I have to make it bigger. So yeah. So we have, let's graph the first one. We have x and x minus 3. So obviously this is a quadratic function. As we know, that if you were to expand the bracket, you'd be left with x squared. So we know it's a quadratic function and it's positive, so it will generally have like something like this, like a U-shaped curve. And we know the roots will be 0 and 3. So let's see, here is 0. We have 3 here. And we know that somewhere along this region will have the turning point. But let's actually solve for the turning point just for the sake of accuracy. So we have this, either way will be x squared minus 3x. So y dash is basically 2x minus 3. And if you were to equate this to 0, you'll be left with, let's just write turning point. You'll have x equals 3 over 2. Let's plug in x 3 over 2 and we'll be left with y, and let's actually solve for this. 3 over 2 times 3 over 2 minus 3, it's basically negative 9 over 4. So we know that it's going to be exactly in the middle, so let's just say somewhere here, and negative 2.25 somewhere here. Let's just say, so we could just do it like this. Keep in mind, obviously this is not the most accurate drawing, but yeah, you could say it will generally look like this. Yeah, let's just leave it with that. And we have x squared and 1 minus x. So we have the roots of 0 and 1. So we have roots 0, and also let me draw this with something of a different color. Let's just say 1 to be here. So we have also here and here. And keep in mind, if you were to actually even expand this bracket, so you could either tell or like identify whether it will be like this or like this, depending on this coefficient, you'll actually realize that it's going to be x squared minus x cubed. So we know that this will be of like the negative type of drawing. And we could realize also that if you were to replace 0, x with 0 to get the y-intercept, you'll also have you're going to be left with a y-intercept of 0 as well. So it will either both will hit at the origin. So we could assume that the drawing is something like this. But let me draw the curves so like it will. So we can kind of assume that there will be 2 points of intersection, aka 2 solutions to these graphs or functions if we were to equate them. So now if we were to actually solve for them exactly, it's set x minus 3 equal to x squared minus x cubed. Am I correct? Yes. So I think so we could take x as a common factor here. So we have x minus 3 equals to x minus x squared. These two will cancel out, so we'll be left with x minus 3 equals x minus x squared. These will cancel out, so we have x squared minus 3 is equal to 0. You just send 3 to the other side or add 3 to each side, so we'll be left with 2 solutions of x of either positive root 3 or negative root 3. And you could obviously solve for the y by just plugging in into each function. It won't matter. So yeah, there we go. Oh, sorry. Actually, there are 3 points of intersection as I actually overlooked. It's obviously the origin as well. I don't know how I forgot that. So we have 3 points of intersection, aka 3 solutions. So we have x's with their both possibilities and 0 and 0. And obviously you just get the y by plugging in into each function. So yeah, sorry about that. So next question we have is 4 over x squared and x squared bracket x minus 3. Okay, apologies. I was just drinking my coffee. Sorry, let's graph them and see how many solutions or points of intersection there'll be. So same steps. We're going to draw the graph. And 4 over x squared can look something like this. Let's just assume it to be like this. All right. And x squared and x minus 3. So the roots will be 0, aka the origin. Because either ways, this whole thing, if you were to just replace it with 0, you'd be left with y equals 0. Let me add y here, because I forgot. And you have x equals 3. Let's just say 3 somewhere here. So it's going to look maybe something like this. Who knows? And let's also get its starting point to see, because if I were to be solving, I don't know if it will go like this. Probably hit here and then just curve its way down, or to just not touch whatsoever. And let me add this 4 over x squared. So let's say 2 is here. This is 2. This is 2 and 1. Okay. So let's solve for its starting point. We could just set its derivative to 0. So obviously this x squared minus 3x, x squared minus 3x squared, apologies. X squared minus 3x squared. So this is basically 3x squared minus 6x. Set this to 0. You can divide the whole thing by 3, so it'll be left x squared equals, yeah, x squared equals 2x. You have x equals 2. And I just realized that I don't know why I assumed it to be negative. It could be something like this. But I don't know if to like, you just never know. Let's just solve, So if x equals 2, if we were to plug in x equals 2 into that cubic function, left with 2 squared bracket 2 minus 3, so it will be negative. So actually there'll be only one point of intersection. Let's just draw it. And the thing is, it will be very difficult to get this point of intersection. The book says it's just this is like a bonus question, you could say. You would not be expected to solve this question in your exam, quote unquote. So although we know that there is one point of intersection or one solution to this question, and yeah, it's just the same thing as simultaneous equations that we went over. It's just graphically finding out the points of intersection or their solutions to their functions. Okay, another question we have is to find the points of intersection of these two functions. So same steps, nothing out of the ordinary. Just graph them. X squared plus 1. We know that x squared is basically like this, and the turning point is at its origin. But since you added plus 1, so the origin will now, or the turning point will now be 0 and 1. And we'll actually talk more about translating graphs, and you'll get to see why. So if we were to assume that this is 1, so this is turning point. And let's go to the next function. We have 2y equals x minus 1. If we want this to be a straight line graph, obviously we need y to not have any coefficient next to it. So we can just divide the whole thing by 2. So I'll be left with y equals x over 2 minus half. So we know the y-intercept for this straight line graph will be at negative half, somewhere here. and we have what it would be at when y equals 0. I think it's at, yeah, at 2. Or pardon me. I think it's at 4 actually. Bro, am I okay in the mind? It's at x equals 1, bro. Okay, I'm tripping. So something like this. Let me just get a different. And yeah, I know my drawing might be off. Maybe the curve has to be a bit wider, but you get the point. Either way, if there is there are solutions actually to this, then I will just redraw the curve. So now if we just equate them together, let's just do it here. I get a different color. X squared plus 1 equals x over 2. Or I could actually just take half as a common factor, then x minus 1. And times the whole thing by 2 in each side to get rid of it. So we could have 2x squared plus 2 minus x plus 1 equals 0. So we'll be left with 2x squared minus x. So these terms are gone. We have plus 2 plus 1, so plus 3 equals 0. So let's put this in the calculator to... I'm getting imaginary numbers. So let's first of all actually get the discriminant of this to see if there are any solutions. So as I said, I was getting imaginary numbers in my calculator. So let's just get discriminant. This is also another way to confirm. So it's b squared minus 4ac. b is negative 1, so we have negative 1 all squared minus 4, 2 and 3. So either way, I don't even need to calculate the actual value of this. I know that this will be less than 0. Because obviously, this will be a negative number, which is way bigger than positive 1. Because the negative will be cancelled out by the squaring of it. So I know this is less than 0, so there will be no real solutions to this. And to also... Sorry, I pressed the wrong button. To also make sure... There we go. There is no real solution whatsoever to this. So, yeah. There you go. This is also another bonus question that was in the book. It's not really bonus, but like it's based off the previous question. However, there's just one difference. Let's say that in the quadratic curve, just so you guys could know, in the quadratic equation we have, instead of having our y-intercept to be known, it's just some arbitrary number. We'll name it a. So it asks, work out the range of values of a such that these two functions have 2 points of intersection. Okay. Okay, and actually for this question, we don't really need to solve anything algebraically since it's based off the previous question. So let's first of all just draw our straight line curve, as that's what we know. So at x equals 1 and y equals half, let's look something like this. Let's just say. And we have x squared plus a. And as we know, a is just some random arbitrary number and it could be anything. And as I mentioned previously, the question wants us to find out the range of which a will... the range of values of a that will give us 2 points of intersection, 2 solutions. So if we quickly look at the graph, you can notice that if we placed the turning point of x squared plus a at the y-intercept, obviously it will cross here, or they will both meet in this point. And either ways, the function of x squared plus a will look like this. So there'll be another point of intersection as well. So now we don't really need to prove it. It's self-explanatory, to be honest. Because as you know, the turning point is here. We'll assume that the turning point is here. Because if you were to even solve this algebraically, I don't think so you'll get anywhere. I found this easier to... I found it just solving it straight away like this easier. So, and you already know the shape of the x, like the quadratic curve, something like this. So there are 2 points of intersection at the turning point of negative half. So we know that at anything, and obviously if you go higher, there'll only be 1 point. No matter how hard you try, there'll never be 2. So anything lower, because either way to let here and here, you know. So we that know that at anything less than negative half, apologies, yeah, at anything equal to or less than negative half, we'll have 2 points of intersection or 2 solutions. Next, we're going to talk about 2 concepts which are kind of similar to one another, where you just basically manipulate how the graph of a function looks like, either by translating it, aka you just change the x and y coordinates of it by either just adding or subtracting, like just to put it in simple terms. And the next concept after this is basically stretching. It's basically like changing the amplitude of the graph you could see by just adding a constant as a multiple, you know, to either the x or y. So first we're going to talk about translating graphs by this way, where if you have a function y equals f of x and then you add plus a in the outside, and please keep in mind where the plus a is over, or it's to the whole function of f of x. So it's basically, it's like saying y equals y plus a, because we could already just assume that y equals f of x is just the same thing. It's y as itself. So the new y, once you add this new translation, it just means that you're adding a to the y coordinates of your function. And for the x, if you want to translate the x coordinates of your graph, yeah, and this is just in vector terms. If you add a to a function like this, you're just basically shifting your graph vertically by a. And the opposite of that is also when you add plus a to the x terms. This way you're shifting the graph horizontally, either this way or this way, but by the negative sign of a. So let's say if you were to have a graph of whatever, f of x, then minus a, this actually means that you're going to add a to each x coordinate of your function. And likewise, if you were to see plus a, you're just going to subtract a to each x coordinate of your function. So for the x terms, when you have plus a next to your x, you just basically do the opposite of it in terms of its sign. And we're going to see here, let's graph x minus 2 and all squared. I forgot to complete it. So yeah, let's graph this function, x minus 2 all squared. So we could already look at it in simple terms. We already know the graph of x squared, which is like this, where the origin holds the turning point. And since we have minus 2 next to the x, that basically means you're just going to add to the turning point. So you can just say like 2 and 0 is the new turning point. 2 and 0. It's going to look like this. But I want to show the proof. Wait, let me just change the pen color. Let's say if we were to actually look at y equals x squared, the original function that we could assume it to be. And let's pick any x coordinate and let's just say 9. No, I mean, sorry, y coordinate 9 equals x squared. So it could either be, so the x coordinate for y equals 9 could either be positive or negative 3. Okay. And now let's see if we were to plug in 9 here, what would this x coordinate look like? So now let's solve, and let's just assume that y is basically 9. 9 equals x minus 2 all squared. So we could just put like square root each side, so we can get rid of the squaring here. So that will be positive over negative 3 equals x minus 2. So the new x terms could either be plus negative 3 plus 2. So it could either be negative 1 or 5. That's like the simple proof of it, where we looked at the original function of x squared equals 9. So x was either 3 and -3. And in our new function, this, we assumed it to be x plus a, whatever. If we're going to look at the standard form of it, we just took the opposite sign of it. So we were going to add 2 to each x term, and that's basically the proof of it. So there you go. If you're going to add within the bracket of f of x, aka you're manipulating the x coordinates, you'll take the negative sign of what you'll do and just add the change to the x coordinates you have already. So yeah, there you go. That's the simplest I could do. So yeah, if we were to graph the function, 2 and 0 be the turning point, and it will look something like this. And let's look at another function as well, but this time we'll manipulate the y coordinates. Let's look at y equals x squared plus 2. A second. You see, now the plus 2 is not within the x. The plus 2 is all to the f of x, aka you can just assume this to be f of x. So the plus 2 is over the entire function itself. Okay, apologies. So the next function we have is x squared plus 2. So as I was saying, the plus 2 is over the entire function of x squared. So what we're going to basically do is that we're just going to add 2 to each y coordinate. So if we're going to, as I said, the original function of x squared, it has 0 and 0 as its standing point. So we're just going to add 2. So at 0 and 2, this is the function of x squared plus 2. Moving on, we're going to talk about stretching graphs. And as I said, or maybe this is a different recording, but in stretching graphs, you're basically just changing how much the graph will either stretch or compress, depending on either way you'll manipulate the x or y coordinates. It doesn't matter. It's just like you're changing the amplitude of the graph. So if we're going to look at this one, y equals a times f of x, and a is just basically the constant that you'll multiply f of x with. This is the shift that will occur. You'll have your x coordinates as it is normally, and you're just going to multiply each y coordinate by a. So each a coordinate will, each y coordinate will increase by a times. So let's say if you're going to have y equals 2x squared, for example, so each y coordinate will increase by a multiple of 2, aka you just y times 2. But the opposite, of course, in the x manipulation of it, if you have y equals f of a times x, your x coordinates will actually decrease by a multiple of a. Basically, it's reciprocal. So let's say if you were to have y equals what can we do it with? 3x squared, or all squared, I mean. So your x coordinates will, each x coordinate actually decrease by 1 over 3. If you want to look at x squared graph as it is, the change that you'll do is that each x coordinate will be multiplied by 1 over 3, aka it will decrease by 1 over 3. So that's it, and let's obviously solve some questions so you can get to understand more. And I'm looking at the question of the textbook, and there's no reason for me to actually like solve anything specific. I just want you guys to see how changing the amplitude of your function looks like visually. So let's say we have y equals x, 2x minus 2 and 2x plus 1. This is the original function that we're going to deal with. You see, so the only changes which happened are to the x coordinates, where basically you have 2x minus 2. So each x coordinate will increase by 2, but also will be divided by half. And you'll see what I mean. So let's say if we have, I want to look at the y coordinates because the next graph we have is 2x. So I want to get a known coordinate. So we have here -1. Let's look at this -1. you're going to realize that for the same x coordinate, the y coordinate will just be multiplied by 2. And yeah, for example, here, this is very prominent, the turning point basically. You'll find that the turning point of the original function of x without the multiple of 2 is around 0.3. And if you look at when you alter its amplitude, it's around 0.6 as well. So that's what I just wanted you guys to see. And the last point covered in the textbook for this chapter is just basically like implementing these concepts into unfamiliar functions, where we can just do one pretty quickly. Let's say I have a function and it's not given to me like its equation or whatnot. I just have the graph of it. So let's say I have a function like this. I want to draw it properly. Something like this, let's say, and I don't know what it is, but all I know is that I am given specific key points within the function. So I have this to be 1 and 4 here. Oh no, sorry. This is 1/4, and this turning point is 3 and 1. And obviously we have the origin here. It's supposed to cross the origin. We have O. We can just name this to be O. And the changes that we're asked to do is, let's pick one. We have y equals f of x plus 1. So let's first of all, we have y equals f of x plus 1. So what this means is that each key point that we have within the graph, we're just going to decrease it by 1. So if we're going to draw a new graph, and I'll just draw it roughly because I don't have an actual scale for this graph that I could draw right now easily. So each key point, so if we have 0 and 0, first of all, we're going to move by order for each key point. 0 and 0, and we're going to decrease each coordinate by 1, x coordinate by 1. So we'll have -1 and 0. And then we have 0 and 4, because if we look here, and we'll have 2 and 1. So we could go 2 and 1 somewhere here. So this is the new function we have. So, and we just want to label, we have -1 and 0. We have 0 and 4. And we have 2 and 1. So yeah, that's basically what it is. I'm not gonna go over the rest of the changes are pretty simple. There's y equals f of x minus 1, and there's y equals f of x all minus 4. So you're just going to basically subtract each y coordinate by 4. There is 2y equals f of x, so y equals half of f of x. You're going to, and this basically changing amplitude. You're just going to get each y coordinate and have it halved. Yeah, it's pretty simple. So yeah, that's basically all that you need to know about graphing functions, cubic, reciprocals, and how to manipulate each of them and alter its amplitude.